So we've got 8.4, which is talking about the determinant of a square matrix. Now, if you watched my video on 8.3 with inverses, determinants are not really taught in 8.3, but I bring it up because it's actually used in that formula. So if you watched that video, then you would have actually heard about the determinant already, because I wrote it in the formula when I was doing the inverses. So every square matrix has a real number, and that real number is called a determinant. So every square matrix has a determinant, and determinants are used to solve systems with matrices, such as using the inverse to solve, or because you need the determinant to find the inverse as one method. They are used to find what are called eigenvalues, which is something that you don't actually learn about until, like, unless you're going to take like a linear algebra class. But that's a special type of, the eigenvalues are special numbers associated with a matrix. There are lots of things in linear algebra, which is just studying matrices, that use a determinant. So determinants are very, very important in the whole study of matrices. If you find a determinant for a system and it's non-zero, that means there is a solution to this system. I wrote the solution has a unique solution when I meant the matrix has a unique solution. My brain was ahead of myself there. Let's correct that. So if you get a determinant of 0, that means there's no solution to that system. Otherwise, as long as you get a number, it could be a positive or negative. That means there is a solution. The most common determinants we work with are 2x2 determinants, and these are the determinant that I referenced in the inverses video. These are actually very, very simple to calculate. It's just a matter of multiplying diagonals and then subtracting them, but you just have to make sure you do it in the right order. So I have a matrix here. I just labeled the positions as A, B, C, and D. And so the determinant is the first diagonal going from top to bottom as you go left to right, A times D, and then you subtract the opposite diagonal, multiplying those two together. So it's like cross multiplying, but you're subtracting, and you need to make sure you do it in the right order. Otherwise, you'll get the opposite sign. We can indicate the determinant by just saying det of A. That's often used in programming, especially if you have a program, let's say you have a library that has built-in math functions. They usually use det to represent the determinant. It's also used with the vertical bars. And these are the same as absolute value symbols. The difference is that you're not taking the absolute value when you have a matrix. So you know whether it's an absolute value or it's a determinant based off of the context, whether you're using a matrix or just numbers. Some textbooks actually put all matrices in bold so you can tell whether it's a matrix or not. So I did that here just so you can see that difference. But that's different from taking the absolute value. So we take the absolute value if we have a single number in there, but if it's like a matrix inside, it's not the absolute value. It is called the determinant, and that's telling you that you need to calculate by multiplying those diagonals and subtracting. So symbols are very important here because there's a clear difference. I'll zoom in here. Between the brackets surrounding a matrix and then the vertical bars. The brackets are just listing the matrix. The vertical bars are telling you to do the determinant. So if you leave off the little ends and you just write vertical bars instead, you are giving something completely different than you intend. So the symbols here are really important, and it's really important that you use the correct symbols when you're working with matrices, when you're showing your work, all of that, so that you aren't writing something that's the opposite of what you mean. You want to make sure you're communicating exactly what you intended. So I've got some examples here to find the determinant. It's basically just a matter of multiplying and subtracting. So we always take from the top to the bottom. So we want to find the determinant of each of these matrices. And so we're going to take -9 times -2, going from top to bottom, left to right. And then you subtract the other direction. Whether you go from top to bottom or bottom to top, it doesn't matter because multiplication order doesn't matter. So if you want to just always do left to right, then you could do top to bottom, bottom to top as a way to remember it. So maybe like top to bottom minus bottom to top, going left to right. Might be a way to help you remember it. So you're just literally multiplying those together. So we have 18 minus 0, and so the determinant of that matrix is 18. So if that matrix was involved in a system that we were trying to solve, that means we would have a solution. Or if you were trying to find the inverse of that, that means there is an inverse. So second one, same process. So we have 3 times -8, and then we always subtract the other direction. So let's do 4 times -3. The biggest issue you might mess up here is just negative signs. So 3 times -8 is -24, and then here we end up adding because the negatives cancel, so we end up with +12. And in this case, we ended up with a negative determinant, and that's completely fine. It just means that, okay, I can find the inverse. There is an inverse to that matrix. That means if this was involved in a system that I'm solving, I can find the system or find the solution. Are there any questions? Finding the matrix of a 2x2 is so simple that I usually don't even bother trying to use technology to do it because I think it takes even more time to type it into technology than to just do the math yourself, you know, because it's like, oh, I'm just doing 2 multiplications. Like I could easily just do that in 1 step on my calculator. So I generally just do these by hand and I don't even bother using technology. Now, I do use technology when you have bigger matrices. And so the terminology here is going to seem a little confusing. So we have these things called minors and cofactors. And technically you can use minors and cofactors to find the determinant of a 2x2 like we just did. But I think it's just unnecessary confusion in terms. It just going into how it works just seems like it's more complicated than you need. Minors and cofactors are used when you have to find, like, let's say you have a 3x3 or a 4x4, or God forbid you have like a 10,000 by 10,000, you would use this process. But generally for those who use technology, because it's cumbersome. It's not easy to do by hand. The bigger the matrix, the harder it is to do by hand, the more calculations you have to do. So basically you have a square matrix, and we call the minor as the determinant of the matrix obtained by deleting the ith row and jth column. So if I wanted to find the minor 1, 1, which would be the first row, first column, you're deleting the first row, the first column, and that leaves you with a 2x2 that then you're going to find the determinant for. And so that is considered the minor. And so you can find the minor for basically anything. I could find the minor of the first row, second column, and I would use whatever I have not crossed out. I could even find the minor of the second row, second column, and that would use whatever is remaining. So you can find in a 3x3 9 different minors. This is just what they're called. And let's say if I had a 4x4, let's call this one B. B1, 1, B1, 2, B1, 3, B1, 4, 2, 1. I don't have enough room here. 3, 1, B4, 1. I'm trying to squeeze it in, but I'll just leave little dots to represent these. If I was to find a minor of something even bigger, let's say I wanted a minor for the first row, first column, I would delete the first row and the first column. I now have a 3 by 3 matrix I would have to find the determinant of. And so then in order to find that determinant, you have to find the minor of that. So to find a minor, you need to find determinants. And if you don't know how to find a determinant of 3 by 3, you have to use this system. So it's kind of recursive. So if you're done programming and you've heard of recursive stuff, that is essentially what this is. If you have big matrices, you keep eliminating rows and columns until you get to a 2 by 2 you can take the determinant of, and then you kind of work backwards. So it's a recursive process, which is why it's great to use technology for this. But as I said, it's very, very time consuming, and we generally don't want to do this by hand. So the minor is just literally the determinant of the smaller matrix that you have. And sometimes to find that minor, you have to find a determinant of even a smaller matrix. Now, the other half of this is called cofactors. And cofactors are referring to the number that you get with the minor, but with either a positive or a negative sign. So there's actually a formula for the minor. And the difference is you have this -1 to the I plus j. It's just going to tell you whether your answer is positive or negative. And it turns out they're going to alternate as you move across the matrix. So if I have the same 3 by 3 and I find my minor by finding, I found the minor of the first column, first row. So I'm looking for, I do the determinant of the non-crossed out things. Then I need to find the cofactor by figuring out, is this going to be a positive or negative answer? And so you have -1, and it's first row, first column that adds to 2. So you're basically squaring a negative, and so it ends up being the same, so it ends up being positive. In a 3 by 3, what happens is that they basically alter sign for these cofactors, whether you're going to get a positive result or a negative result. They just alternate. So that can help you remember, okay, so this is going to be positive, this is going to be negative, because they alternate. So that's what the cofactor is. The cofactor is basically the determinant, which is the minor for that smaller matrix, and then including whether it's going to be positive or negative. So that's just terminology. And what this brings us to something called Cofactor Expansion. And that is the process of finding the determinant for things that are bigger than 2 by 2. So that is called Cofactor Expansion. And the key here is that is the sum of the entries in a row multiplied by their cofactors, essentially. So to find the determinant of a square matrix, the cofactor expansion, so it's the sum of the entries in a row multiplied by cofactors. You can do this for any row. So if you have a 3 by 3, you can do it for the first row, but you can also do it for the second row or the third row, or, sorry, something's popping up halfway on my screen. You can do it for the third row. It doesn't matter, but when you're doing cofactor expansion, you pick one row. So only pick one row. And so this works for larger matrices in order to find the determinant. Usually it's used on things larger than a 3 by 3 because a 3 by 3 kind of boils down to a pattern that you can remember. So that's simple enough. And for a 2 by 2, we already have a formula for that. So we don't need to use this crazy system or whatever for the 2x2. So this is cofactor expansion. I'm just going to kind of work out how you find the determinant of a 3x3 using cofactor expansion. I do believe I forgot to multiply by, yeah, I thought I forgot to put in this, that you need to multiply by the numbers in the row as well. So here I just have a 3x3 matrix, and I'm just going to use the first row for the cofactor expansion. So if I want to use the first row, first column, I'm finding the minor of the 2x2 that's formed. And then you move on to the next one. So that would be M12. So you find that minor of what's left over, you find that determinant. And then you have your third one, you find the determinant. And it's going to be positive, negative, positive for that pattern. And this is just have the math here. I don't care so much whether you're following the math or not, because this is just explaining how it works. And then the parts that I forgot is that you need to multiply each of these by the number in front. So we've got A11 needs to be multiplied in front of there. This needs to be multiplied by A12. And then this third one is multiplied by A13. So I forgot to, when I typed it up, I was doing a lot of copy and paste, and I forgot to put those in to actually show that you're multiplying those out. So that would be how you find the determinant of a 3x3, is doing this process. And you can do the same thing with a 4x4, where you then have to find the determinant of a 3x3, and it gets into this messy kind of thing, just completely messy. But basically, when I have a 3x3, I just think about the pattern. So that's what I'm going to think about here on this, because you're not going to really be doing this by hand most of the time. It's important just to kind of understand the pattern of how it works. And I'm actually going to see if there's any ways that any websites that kind of color code this that I can steal from. Not really. I'm gonna just pull it over. So I thought, I'm like, is there some color coding I can do? And this is the pattern that I'm talking about here. It's on Math is Fun. I don't know if that pattern is any more complicated there, any easier. But I'm going to try to do patterns. So it's basically, I remember that I have positive, negative, positive. And I always think about it, if I have a 3x3 matrix, I'm crossing out the first row, first column, first row, second column, first row, third column. And so, and then, oops, I didn't want a highlighter there. You're multiplying them by the numbers that are basically at that cross-section point. That's how I visualize it, is that I take that cross-section, A11, and then I got my determinant in that area that I'm multiplying. So that would be A22 times A33 minus A23, A32. Then I always remember that my next one is a minus, and then I'm going to take that cross number, A12, and then I'm multiplying this diagonal, ignoring my crossed out stuff. So it would be A21 times A33, and then A23 times A31, or however order you want to multiply that. And then we add in the third one. My cross section that I crossed out is A13, and then you multiply A21 times A32, and then A22 times A31. So that's how I think about it as my pattern, so that I don't memorize this formula. I memorize the sort of the pattern of how it works, because the formula gets sort of complicated. So I don't know if this helps you at all. And you are completely welcome to use technology to do this, but this is how I think about it and how I look at the patterns. Do you guys have any questions on these patterns, or maybe, you know, do you think looking at it this way helps you or makes sense to you, or do you think, you know, I am going to do an example, so don't worry, but I just want to know where are you at with this and looking at that pattern.
I think it looks like it's pretty easy to understand doing it this way.
Okay. Yeah, I like to follow patterns. It seems easier than what you got from the textbook. Well, that's good. Yeah, I mean, when I was reading the textbook, and I have the textbook open, and I'm trying to see how they're explaining this, and they're not like showing you the pattern like I'm doing here, and I think that's what makes it harder. And I'm like, no, I'm looking at this visually because this is how I figure it out. But, you know, I encourage you guys to use technology to double check your math as well, so that, because it's easy. You can make a sign error here and it could mess up anything. So because I want you guys, I want to encourage you guys to use technology here. I'm not going to go into like tons of examples here, but I did want to demonstrate with numbers finding the determinant of a 3x3 is in addition to those 2x2s. Anything larger, don't even bother doing it by hand. Just use technology. So if we want to find the determinant of this matrix, we start with our first number 1, and then so we want to basically cross out first row and first column. We're finding the determinant of what's remaining there. So I'm going to do 2 times 4 minus, and the 2x2 determinant is always subtraction, and 5 times -6. Then I know my next one is going to be minus, because the pattern is always going to be positive, negative, positive. So then I can just use, this is the wonderful thing about using a tablet, or if you have erasable pens, you can just erase what you did so that you don't have to rewrite it. So I'm looking at -1 here, and because we're subtracting that -1, I now have that double negative there. Now my determinant, I'm going to take 3 times 4, subtract 5 times 4. And you can kind of get lost in the parentheses, so that is something to be careful about. And then I'm going to erase that, and so now I'm looking at 0, and I'm going to take my row times column. So because it's always going to be a plus, and now it's going to be a 0. Now this is going to cancel out, because 0 times anything is 0, but I'm going to still write it. 3 times -6 minus 2 times. And now we're going to simplify the math. So going left to right, multiplying by 1, that's not going to do anything. So I have 8 plus 30. Subtracting a negative, so that's going to be plus, and that was a 1, so that's not going to do anything. So then I'm going to have a 12 minus 20, and then a 0. 8 plus 30 plus 12. Oh, it would help if I actually typed a 3. And I can actually put 20 in the right order. I just typed 0, 2 instead of 2, 0. This comes out to 30 as our determinant. Now, I said that with the cofactor expansion, what you can do here is that you don't have to, you can use any row. So in a different color, I'm going to show you what that looks like, and we should get the same answer here. So let's say instead of the first row, I use the second row. So I wanted to work with 3 instead. So I'm going to have 3 in front. And when I'm crossing things out, it's going to be the second row, first column in this case when I'm crossing things out. So my determinant will be -1 times 4 minus 0 times -6. I'm still going to have my minus. And then I'm going to move on to the next number, which will be 2. And so using the second row, second column, to find the determinant of that 2 by 2, it's going to be this 1 times the 4 minus 0 times 4. Then I have a plus. And now move on to the last number 5. That's the last column, second row. So I'm going to have 1 times -6 plus -1 times 4. So now we want to start simplifying. So I have a 3 times -4, and then that's just 0, because -0 times that. Minus 2, 1 times 4 is 4. Again, we're going to be subtracting 0. And then we have plus 5. And inside, we're going to have -6 plus -4. So I get -12 minus 8 plus 5 times -10. -12 minus 8. I have, where did my sign error go here? Somewhere I have a sign error because I'm like, wait a minute here. Because that should be last parentheses group. Okay, thank you. Yeah, I'm like, it has to be there. 1, -1 minus, wait a minute, minus. Okay, I need to double check here. So I've got 1 times -6 minus -1 times 4. 1 minus, okay, so that should end up minus should be plus 4. So then that ends up here. That's -2. That's still not going to get me to 30. Do I have another sign error somewhere? 3. This is why I usually don't do it by hand. -4 minus that's going to be 0. Minus always. Oh, I see what I forgot. So I forgot that when you're in the middle group, the signs are negative plus negative. That was the other. There should be multiple errors here. So because I'm so used to doing the top where it's always plus, negative, plus, but in the middle group, it's the opposite. So I change, so this should be, so that's a negative, so that's a positive 12. Then that's plus 8. And then that ends up, that's a plus, wait a minute, okay, so 12 plus 8, okay, so minus, oh wait, nope, I changed that to minus, that's a minus, minus, that becomes a plus 10, there we go, okay. They match, so key thing, I never do that second row. If you switch to a different row, like if you do the second row, the signs are inverted, so it goes minus, plus, minus. But I always do the first one, so I didn't even think about that. You can see, assuming that you get all of your signs correct, that you do get the same answer for the determinant, no matter where you start there. So I got 30 for both, and I knew that I had made a mistake because I'm like, wait a minute, this is not coming to 30. Somewhere there's a mistake, you know, so then I had to go back. So it's important to double check your signs, and use technology to double check yourself as well. I think that's especially for a 3x3, it seems like such a simple calculation, but it's so easy to make a little mistake, and then that can throw your whole thing off. So that is how you find that determinant. Do you guys have any questions? I know earlier, and I think I put in an announcement, I suggest to the Desmos matrix calculator. So if you want to find the determinant of the matrix, you can use this determinant button here. So we can double check our answer here. So I have A equals, let's see, we have 3 rows, 3 columns. Oh, they already named it A. So I'm going to just double check our math by plugging in our numbers. For a 3x3, it's actually probably quicker to use a calculator to do it than to do it by hand. So I've just defined A, and then the determinant of A, good, 30. So that was a lot faster than doing it by hand. For a 2x2, it's quick to do by hand. I don't even bother with technology. But for a 3x3, even though the process isn't too bad, it's definitely quicker to use technology. And you get the same answer.